So good evening. Thank God, like now you just had coffee or tea after a good lunch. So no one will be sleeping for this session. Again, my request to the backseaters, please join on the front seats. It's good to have because we are going to take flipped photo now. So next session we have by Nutan. So next session is by Dr. Nutan Lime. She is an associate professor in the computer science department of IT University of Copenhagen, Denmark. Before this, she was associate professor in the Department of Computer Science and Engineering, IIT Bombay, India. She finished her PhD at the Institute of Mathematical Sciences, Chennai, India in 2009, she did a one-year postdoc stint at TIFR Mumbai before joining IIT Bombay in 2010. Her research interests are in theoretical computer science. Specifically, she is interested in algorithms and complexity theory. Her recent research has focused on algebraic complexity theory and lower bounds. She is an associate editor for ACM Transaction on Computation Theory and SIAM Journal of Computing. She received the IRCC IIT Bombay Research Publication Award 2019 and the Best Paper Award for Fox 2021. She contributes to teaching activities at IIT Bombay. She has been on program committee of reputed computer science conferences such as STOCK, Fox, ITCS, and ICALP. She has been part of the Association of Computing Machinery in many different capacities. Presently, she is the ACMI-W Regional Activities Co-Chair. She was associated with ACM India as the Vice Chair of the ACMI-W from 2019 to 2021. She was also the Treasurer of Indian Association of Research in Computing Science, India from 2018 to 2020. Nutan is the Outstanding Contribution in Computing Women 2023 awardee, and now I'll welcome her to talk on the limits of efficient computation and algebraic complexity perspective. Sorry, Nutan, I flipped your slides. Please welcome.
Thank you so much for a generous introduction. And thank you everyone for staying back so late and attending this talk today. Am I audible? Okay, great. So, like the title suggests, I'm going to talk about limits of efficient computation, but while the mouse was moving forward, you already saw some efficient computation. Namely, computation was going on at the background while we were talking. So we all know this world of computation. In ACM, we are no strangers to how much computers have changed our lives today. And it all started maybe in the 1940s when very preliminary computers were built. All they could do was very simple math, maybe some calculations. But already within 60 years or so, which is very fast, we were holding a huge computer in our palms. And it could do many, many things. It could compute, for one. It could, for example, communicate. You could play songs on it. You could take pictures on it, and so on. And now there is also this buzz about quantum computation, which may take us even further by leaps and bounds in the coming years. So there is a lot of promise from extremely efficient computation. And we all are here because we believe in this power anyway. However, let me flip this question around a little bit for the purpose of this talk. So let me ask you, what are the limits of computation? I know I'm like a spoiler when everybody is so happy about computation, but it's a good check to have to know whether we are being extremely optimistic about what we can do with computation, and these are realistic checks we should make every time computation makes advances. Okay, so what are the limits of computation? And in fact, this is one of the central questions studied in the area called complexity theory. This is the main area of research that I work on. So here is a very, very interesting and surprising statement in computability. It says that there exist problems that cannot be solved by any computer, right? No matter what amount of resources it will use. So for example, visualize all problems as this bigger blob here, and the problems that computers can solve as this smaller blob. Yeah? Well, the two blobs don't have to be different, right? Maybe every problem is indeed solvable by a computer. But what this statement here tells us, and it's a known fact, that there are problems that are actually not solvable by any computer. Yeah? When I first heard about this, I was actually in college because we had a professor who taught us computability, and he told this statement very casually in class, and I was stunned by this because I really believed in computation at the time. So algorithms, fast algorithms, and I just felt like we could solve everything. But that wasn't the case, and this statement was very fascinating for me. We have seen such statements in school actually, not about computation, but in mathematics. For example, all of us know that square root 2 is not a rational number, right? So to put it in the words of computability or computation, I could say that my model of computation is representing any number by a ratio of two numbers, A divided by B. So that's my model of computation. Yeah, give me any number, that's the input to the user, from the user. My model of computation is I want to represent that as a fraction. One integer divided by the other. And we all know that this model of computation cannot do that for square root 2, right? So this is another way to show that real numbers are actually different from rational numbers, right? In fact, we've seen this also in school. Suppose I give you a ruler and a compass, and I ask you, so these are the operators, yeah? This is your model of computation. You have only two operations that you can use. You can draw lines or you can use a compass. Now I ask you, can you bisect an angle just using these two operations? You can use them as many times as you like. Yeah? And of course, we have seen this algorithm for doing it. Yeah? What you do is you draw this compass from the common point, and then you draw two curves, and then you draw a line. That's the bisection. Now I change the problem a little bit. You still have the same computational power. You still get a scale and a compass, but now you want to ask, can I trisect an angle? Yeah? Just using these two operators. And it's very fascinating that actually it's known that you cannot do it. Yeah? So it's also one of these statements where there is a set of computation a set of operators that you apply to a class of problems, and in fact that class of problem is not solvable by it. Yeah? This is saying that there are things beyond computation if you have some restricted operators to start computation with. Yeah? Fair enough. I could also do kind of a thought experiment where not only do I bound the operators that you're allowed to use, but I also say that you're not allowed to use these operators more than 100 times. And then I can say, can you now say that certain functions are not computable if you use these operators only 100 number of times, right? So for example, the problem that I'm working with is sorting n numbers. Okay, we've all done it. And in fact, it's known that if you only use your model of computation among different things, you're allowed to maybe, read a number from a list or write a number or something, but the main thing that you pay money for is to compare two numbers. As soon as you have to pay money for comparing, say 1 rupee per comparison that you do, then it's known that you need at least n log n comparisons to sort these n numbers. Some of you may have actually seen a proof for this in your data structures or algorithms course, right? And this is also, in a sense, trying to prove limit for computations. Yeah? So this talk overall is going to be about this dichotomy, or rather, I wouldn't call it dichotomy, two sides of the same coin. Yeah? On the one hand, we want to make advances in designing better algorithms. That's, of course, where we want to make progress. And then there is this sanity check where we ask, is this possible always? Yeah? So you'll see this theme recurring through this talk. And what I would like to do from here on is to tell you a little bit about my research that aligns with this theme. So everybody okay so far? Thank you. So like we said, limits of computation is indeed a central theme in complexity theory. And in a way, everything that I learned about complexity the first time was from these two people at the Institute of Mathematical Sciences, where I did my PhD. And I started my PhD actually 20 years ago now, 21 years ago. 2003 is when I started it. And on the left, you see V. Arvind. You may have met him at some point, and Meena, who's here, so you can meet her. So they both taught me complexity 1 and complexity 2 when I was a PhD student at IMSC. And in fact, later on, Meena was kind enough to take me as her student when I actually didn't know much about any of this. And so a lot of my learning in the beginning happened from conversations and the lectures that I got from both of them. The point of saying this was that while I knew this overall theme that, oh, if I have a compass and a ruler, I cannot trisect the angle easily, and things like that. These are the statements we often see, but complexity theory in a way gives a direction to this way of thinking. And that's the research area that I'm going to talk about now. Yeah? So, why should this be attractive? Why should we study limits of computation? Okay, it's one thing that you want to do a sanity check whenever somebody comes up with an algorithm. That's a decent cause. But then, is that all? Actually, no. Because there is this very important question that has now become very famous. If you solve this question, you get $1 million. I'm not joking. Yeah, this is one of the $1 million questions called the P versus NP question. Yeah, this is also a question that fits exactly in this theme. Yeah, what can I solve using polynomial number of operations? Yeah, for sorting we saw we used n log n comparisons. Now I'm not saying comparisons, I'm saying any operations that a computer can perform, and I give it not n log n time but n to the c for any constant c amount of time. And now I ask, what can a computer do with this much resource and what it cannot? Yeah? So that is this question that that's a vague interpretation of the question P versus NP. P versus NP question is slightly more specific, where you make a distinction. Somehow the colors are not visible. So there are these two circles. Please try to imagine them. There is a smaller circle that contains efficiently solvable problems, and there is a bigger oval that contains everything. I don't know, it's not so visible from where I stand. Maybe it is visible to you. No. It's visible to people on the Zoom call. Right? So, and it's trying to say that there are these problems that are efficiently verifiable, that those are the NP problems, and then there are problems that are efficiently solvable, and then you're asking, is there a problem that's, are there provably problems that are efficiently verifiable but not efficiently solvable? Yeah? So, in my research theme that I will try to put forward today, we give a twist to this question where now the objects that we try to compute are some specific objects. Yeah? These objects are polynomials. So what are polynomials? all of us must have seen some polynomials somewhere. For example, this is a polynomial all of us may have seen in school. Yeah, how to find a root for this, for example, is a question that we try to answer, or maybe some other related questions about this, right? So you may have seen this polynomial before. So this is a univariate polynomial in that it has only one variable, x. All others are some constants. And then its degree is 2. Here is another example of a polynomial. Here the number of variables is 3 and the degree is 2. Yeah? And what I show here in these two lines are two different ways of computing the same polynomial. Yeah? One way is you compute every monomial in the polynomial one by one. Yeah? This looks computationally extremely expensive. On the other hand, you could do some pre-computations or some cleverer computations and instead compute it like on the second line on the slide. Yeah? In which case, actually you might end up using much fewer operators overall. Yeah? So the task is the same, right? We are trying to compute polynomials now, and we want to ask how quickly can I compute or how efficiently can I compute a given polynomial. Right. Yeah. So these are the kind of questions that recently I've been working on. And you may, there are very interesting natural problems that exist that we all try to solve, which can be coded up as questions about polynomials actually. So take for instance this graph. It has 5 vertices, 0, 1, 2, 3 and 4. It has directions on the edges, and I could potentially write this graph down as an adjacency matrix, yeah, instead of just a graph, where I put a 1 in an entry in the matrix if there is an edge from the vertex in the row to the vertex in the column. So for example, there is a 1 between in the cell 1, 2, but there is no 1 in the cell numbered 1, 1, and so on. And then, in fact, I could just open this up and make multiple copies of this. Again, some colors are missing. I don't get this. Yeah. Where what I'm trying to do here is between two consecutive set of vertices, there are edges, and these edges are exactly reflecting what were there in the original graph. Now if I do, this is like the A-star algorithm for finding reachability that some of you may have seen before. Yeah, but just for fun, instead of 1s and 0s, I could in fact put variables in the place of the entries where there were edges before. So where there was a 1, I put a variable to indicate that in fact this 1 is now replaced by this new variable. And so one can actually write the original problem of trying to find, for example, reachability in this graph as a question about these polynomials. Yeah? At first sight, it doesn't look the most natural thing to do. Why don't you just do the A-star algorithm and be done with it if you want to find reachability? But you may notice that if I do this slight generalization, maybe this polynomial can even hide information about how many paths there are from a vertex to another, for example. Yeah? So there are advantages sometimes to go over to this domain of polynomials and ask the same questions that you would have asked, for example, reachability in the setting of polynomials. Yeah? And then, as always, we need to define a model of computation. For trisection or bisection of angles, the operators were compass and ruler. For computing rationals, the operators were representing numbers by ratios of 2 integers. In this case, people have studied different models of computation. Here is one example where you have just multiplication and addition gates, because that's all polynomials really need for computing. That's all we need to compute a polynomial. A plus gate and a multiply gate used several times in some complicated way. Yeah? So this is called a circuit. It's nothing but it reads the variables. It may read some numbers. I've not written those, but x1 could have been 5 or something like this as well. And then you have multiplication gates, addition gates, and so on. And now I want to ask, what can a circuit of a certain size do? Or I could ask, what can a circuit of a certain depth do? Where depth just stands for the number of cascading layers, and the size stands for the number of operators I use. Yeah? Sometimes, because the cascading is happening in a way that you have a plus gate at the top, multiplication in the middle, and then plus again, such circuits are also called sum product sum circuits. Yeah? Very intuitive name. This is a very good shorthand to talk about in the rest of the talk. Yeah? And just throwing in a definition, if this complicated machinery looked like a tree where there were no edges going out from the same vertex twice, then such a computational model is not called a circuit, but instead it's a more special form of circuit called a formula. Okay. So we have circuits and we have polynomials. Let's look at a simple example. This example generalizes the example we just saw a couple of slides ago. Now I have n variables. Yeah? And I compute every possible monomial you can with these n variables. So you have a 1, you have a x1, you have a x2, all monomials of degree 1, then you have all monomials of degree 2, then you have all monomials of degree 3, and so on. Yeah? That's what the polynomial on the top is computing. And you can see that it's being computed by a circuit which is plus followed by multiplication, because it's just sum of monomials. And you can see that you require 2 to the n of them because there are so many monomials in this polynomial. But instead, we can do what we did in the previous example. We don't really need to use 2 to the n operators. All we can do is use order n operators. Yeah? So here I'm giving you an efficient upper bound. Yeah? Good, fast algorithms. And then later we'll ask a question about, is this optimal? Yeah? So this is a theme that will recur. So in general, in the field of complexity theory about polynomials, we ask questions like this. How many operations are necessary for computing a specific polynomial? Yeah? And in this case, you could also observe a little bit more about these two polynomials. The top polynomial has a circuit which is of depth 2, and the next one also has a circuit of depth 2, but its top gate is slightly different. So it's not a plus gate at the top. So if you just hypothetically assume that there is a plus gate at the top, then this is a depth 3 circuit. Yeah? And you could ask things like, can increasing the depth of the formula or a circuit or the computational model buy you any more power? Yeah? Okay. So the part of the, so to summarize the part about polynomials that I talked for the last 10 minutes or so, it's this one slide. We are asking questions about problems about polynomials, and they are important because they arise in natural settings. The questions we ask are about how many resources a model of computation uses to compute these polynomials. Yeah? And the resources in this case are size, depth, etc. of these models of computation. Yeah? Again, some shapes are missing on the right hand side. I even see like a faint edge here, but yeah, for all practical purposes, it doesn't exist, I think. So now I'm going to present some of the results that I have had in the last 10 years or so along the themes. of depth of a computation. Yeah? So all of them fit into this. I'll try to bring back the theme about P versus NP before we close this talk. So I told you what the primary area of research does. That is, it studies polynomials and resources required to compute it. Now, for the next, 10, 12 minutes or so, I will take a detour to take you through some of the results I've had. And if you want to switch off at this point, fair enough. But then I'll bring you back to the important question of the area, which is this P versus NP question, and relate it to the questions to polynomials, questions about polynomials. Yeah? Okay, so here is the detour now. Shapes missing. So here is a very, very interesting upper bound result or algorithmic result. It says that give me any polynomial, say it is being computed, say it has n variables, and it has a formula computing it of size s. Then the result tells you that it can actually be shrunk down to depth log s. Yeah? A formula of size s could potentially have depth s or order s by 2 or whatever, right? But you can actually you can always shrink it down to log s, yeah, without blowing up the size too much. It's a very interesting algorithmic result. Yeah? And like I said before, as soon as I present an algorithmic result, the question at the back of your mind should be, is this optimal? Yeah, that's what complexity theory asks you to think about. Is this optimal? So are there limits to depth reduction? Yeah? Can you maybe go down to depth even smaller? And what does it mean for a computation to be shrunk down in depth? It means it can be computed in parallel very efficiently. Yeah? Something that was probably looking like a very long sequential computation, now you're saying can actually be shrunk down to depth log s. This is a very interesting algorithmic result, as I already tried to emphasize. And now you're asking, can I shrink it down even further? If I can, then it's even better algorithmically, right? So indeed, it's not known whether we can or we cannot. Yeah, this question is wide open as the P versus NP question. Actually, for this you don't get $1 million. Yeah, but in some special cases, for example, in the case of multilinear formulas, what is multilinear? It's a polynomial where every variable appears with degree at most 1. Like first is an example of a multilinear formula, the second one is not. And there is actually a thought bubble there that you cannot see. Yeah? And a formula is multilinear. The model of computation is multilinear if each gate computes a multilinear polynomial. So, previously, in a couple of decades ago, the following result was proved that you cannot improve the depth reduction to beyond this threshold. Yeah? The number is not so important. It's just saying you cannot do depth reduction to arbitrarily small depths. Yeah? Where is the bottleneck is that weird function. You can forget about it. Yeah? But what we really wanted to say is, can you actually not do anything better than log s? And we were able to say that in one of our papers for the multilinear case. That indeed, if the formulas are multilinear, you really cannot expect a better algorithm than log s. Yeah? Then you can ask a fine-grained question about a similar nature. You can ask, what if I just want to reduce the depth of the formula by 1? Yeah? I give you a formula, like in the example I showed you, there was a sigma pi sigma formula. Now I ask you, give me a sigma pi formula. Can you do it? And well, in general, if you are trying to go from depth delta plus 1 to depth delta, there is usually an exponential blow up. What do I mean by that? Let's just look at a simple example. Suppose I gave you the quantity on the first line. Yeah? It has plus operators at the very shallowest level of its computation, and they are combined together by multiplication operations. Yeah? But now I'm asking, can you do the other way around? Yeah? Can you have a plus operation at the top and multiplication operators at the bottom? One very simple way to do that is just open up the brackets. That's all I'm trying to say, right? And this will incur exponential blow up. Is this optimal? Yeah, you could always ask a complexity question when you come up with an algorithm. And again, we do not know in the most general case whether this is doable or not. In some situations, same as before actually in the multilinear situations, it is known that quasi-polynomial blow-up is essential. Now, if you don't know what quasi-polynomial means, it's not important. It's showing some sort of a bottleneck to proving better upper bounds. And then in a follow-up work, we were able to show that exponential blow-ups are actually essential. But all of this in this very special multilinear case. Yeah. Then there are many other results about reducing depth of computations. Yeah. We are still on this detour about depth of a computation like I told you a few minutes ago. So you have a polynomial, so this is a well-known result. You can see that the result to its optimal level is because of all these works from the past. And I'm sorry that I'm not reading out every name right now, but that is just in the interest of time. You can always come and ask me or any other experts for the references. So what this result says is that if you have a polynomial p of x on n variables of degree d that is being computed by a circuit of size polynomial in n and d, then in fact it can be computed by a very shallow circuit, just plus multiply of this weird size. Yeah, again, the quantity in red is not super important, but just think to yourself that if you had n variables and d degree, then the most obvious upper bound is n to the power d. So this is saying something slightly better, which is n to the power order square root d. Yeah? So it's giving a non-trivial upper bound for a computation which works in depth 4. In fact, the result carries over to depth 3, very beautiful result, and one of the authors for this is with us, Neeraj Kayal. He's famous for many beautiful results. And this result says that in fact you can go down to depth 3 without blowing it up any further. Yeah? So you can actually turn any polynomial into depth 3 if you are willing to spend those many operations. Yeah? Now you know what's coming next. Is this optimal? Right? So what are the limits to depth reduction? And there were many results known. In the most general setting, this was the best result known before our work, that you require, again, these exact functions are not so important. What they're trying to say is that we can do something in n to the square root d operations. How many are essential? Are all of them essential? Well, previous results said that at least n cube is essential. Yeah? The functions are far apart if d is very large and close together if d is small. Then, for very special cases, for example, in the homogeneous case, again, a bunch of people contributed to this line of work and obtained the optimal lower bound. That is to say that in homogeneous setting, you cannot improve this. Those many operations are just essential. And then, more recently, we were able to prove this couple of results, which showed this tightness in the most general setting as well. Yeah? And then there was some, this was a result that got some recognition, right? So that was my detour to, through some line of work that I have contributed to, and it's super interesting, obviously. That's why I even talked about it. But now to bring the story back to where we started. We talked about the P versus NP question, and it is an important question in complexity theory because complexity theory asks questions about limits of computation. So, in a similar spirit, for computing polynomials, people came up with an equivalent question that talked about efficiency of computing polynomials. Yeah? And that question is now very well known, called the VP versus VNP question. Again, there are two circles here, two ovals here. The inner oval encompasses the smaller class, believed to be smaller class, VP, and the bigger oval encompasses this class called VNP. Yeah, just like the P versus NP, this is VP versus VNP. VP is believed to be weaker than VNP. So we believe that there exists this polynomial that sits inside the class VNP that's not inside VP. And why is this called VP and VNP? It's because the questions were proposed by Valiant, whose name starts with V. So he didn't name them. Others named this question VP versus VNP. But it's quite an important question now. It was stated more than 4 decades ago by now. Yeah. And just to give you a context of what VP and VNP stand for. So VP is a class of all those polynomials that are computable by polynomial size circuits. So this is not exactly a definition because I'm missing a key point here about these polynomials having polynomial degree. But that's a technicality. For the purpose of this talk, I will not emphasize it. On the other hand, what are VNP polynomials? Again, with a little bit of liberty, this is not the exact definition. This is a class of polynomials such that if you give me the name of any monomial from that polynomial, let's say you say it's x1, x2, x3 square, then using a very small amount of computation, very efficiently, I can tell you whether it appears in the polynomial or not. So is its coefficient 0 or not? And in fact, I can even tell you what its coefficient is in that polynomial. So for all polynomials where I can tell you that easily compute the coefficients of every given monomial, this class of polynomials is the class VNP. Okay? So it's very similar to P versus NP. Yeah? Because in P, it's a class of problems that are solvable efficiently, and NP are the class of problems that are verifiable efficiently. So it's very similar in spirit. So we want to attack this problem in algebraic complexity, just like everybody wants to attack the P versus NP problem in the general Boolean computational setting. And how far have we come in trying to do this? So again, by the depth reduction results I told you about earlier, something very interesting is known. If you can show that there is a polynomial in this bigger class VNP such that no circuit of that size, yeah, you're looking at a quantity that sort of looks like n to the 0 point something more than half, and that's all it is, right? So if you give me, there should be like a omega there. Yeah, sorry about that. That's a typo. There should be an omega there. So n to the omega of this size, for a polynomial, if you can prove such a lower bound, then you will in fact show that VP is not equal to VNP. Yeah, so proving such a lower bound, and very similar lower bounds we were talking about just a few slides ago. So saying this will solve the VP versus VNP question. Again, a little bit of a bummer that this does not give you $1 million, but that's fine. Yeah. And then where are we? We are actually able to get a lower bound of 0.5 there. So if you are somehow able to improve this lower bound from the yellow box, well, the yellow box is not quite visible, but this little thing that appeared to the left of the arrow, to the one above, then you would have solved an important question in algebraic complexity. Yeah? So that's where we are right now. So this is also sort of saying that we are at a very interesting juncture, perhaps. One never knows, obviously, but and so there may be exciting things coming up, or there may be approaches for solving VP versus VNP. Okay? So that's really technically what I wanted to say here. But I would like to close with some future directions. So for this, I sort of view this whole adventure, again, I don't know how to make you see this actually. So I think a little bit is visible. It's like a mountain that I'm trying to visualize here. To the top of it is VP not equal to VNP. And of course, the mountain doesn't quite end there, right? The slides sort of don't give me enough room, but there should be like P versus NP sitting much further up from there, right? So this is not the end either, but suppose that's the goal for now. Suppose VP not equal to VNP is the goal. And in terms of what I have just contributed to, there are many, many results that one could talk about in this region. But for example, we know something now about these circuits which have constant depth. Yeah, depth 3, 4, 5, whatever constant you pick, I can say something about it here. So we need to close the gap between these. Yeah? And one of the two results that I mentioned sort of improved the first one slightly, but in this weird multilinear model again. But really, the upcoming next goal should be, for people working in the area or getting excited to work in the area, is formula lower bounds. That is, all these small depth circuits that we were talking about can actually all be captured by another model of computation called formulas. Yeah? I told you about it many slides ago. I don't expect you to remember them, but they are weaker versions of circuits. So P versus NP asks you, can you show something that's not computable by any polynomial size circuit? Now I'm asking you, can you at least show that it's not computable by polynomial size formulas? Yeah, which is a weaker mode. So this would be sort of things lined up forward on the path. And I'm not going to talk about any of the other things, but of course, there are many, many, many interesting things that are going on in complexity theory that I try to keep up with, if not contribute to, but have contributed to in the past, such as structural complexity, space bounded algorithms, Boolean circuit lower bounds, distributed computing, structural algebraic results, and so on. So this is just to say that I just gave you a very thin slice inside complexity theory, and inside that just what I'm focusing on, but there's so much else going on. And yeah, think of this talk as an invitation, at least to the younger crowd, to take up complexity as a future option. Yeah, thank you. So first question is whether this has any bearing on, so resolving VP versus VNP, does it directly help P versus NP? So what we know is that resolving it will not immediately help, but it is in a way a step towards proving P versus NP. In that, there is a result by Berkey sir from 2000 that says that this problem is philosophically easier than the P versus NP problem. So if you hope to prove P versus NP, kind of you should have been able to prove VP versus VNP. Of course, it may not go this way. The second question was about distributivity. So I'm assuming that there is a plus gate at the top, then a multiplication gate, then a plus gate. So this, as was rightly pointed out, assumes that there's some level of distributivity that we assume on the underlying algebra. And actually, people have studied models where you don't assume distributivity, you don't assume commutativity, you don't assume associativity, and they have results there. So indeed, yes, people have considered that. I can point you to. There are very few papers in that domain. I mean, in the non-commutative setting, there are many papers again, but in the non-associative and non-distributivity, I think non-distributivity, I don't even recall anything, but yeah, for some other kind of algebras, for non-associativity, for example, there are results. Hi, nice to meet you.
That lovely story about what excited Nutan when she was in class in this domain. What do you think we should be doing differently, if anything, to excite the new Nutans who are sitting in class? Yeah?
Yeah, I mean, you are the expert in answering this question as well. I know far too less compared to you about this. I don't know. So, personally, for me, role models really help. So, just being able to see other people do this thing and actually have like a path ahead of them, this helps. But of course, we can't imitate that in a classroom. So, for a classroom setting, yeah, I think math can be, you know better than me that math can be taught so much better, right? So yeah, I think there are many ways to improve math teaching. My feeling is that people who are super interested will anyway, find a way. But I think it's for people who may not start out interested and give up because nobody kind of inspired them. So yeah, it's a very difficult question to answer, but yeah. Thanks.
Hi, Nutan.
Yeah,
It's very
hi.
difficult to like put things which are very complex in an intuitive way, and you have done that. So,
Okay,
thank you for doing that. My question is, what sort of techniques are used to prove these lower bound results? And that's the first question. And another question is that, so in complexity theory, people are looking at this average case analogs of P versus NP.
Yeah.
So, are there average case analogs for BP versus VNP as well?
Yeah, very, very interesting questions. Again, so the kind of techniques that are used, I would be using a very broad brush to say this technique or that technique, but there is actually one technique that I can talk about, which is used in many, many of these lower bounds, which is to analyze, essentially, it boils down to the following, what shall I say, proof outline, where you design something called as a measure. Think of it as a weighing scale. You design a weighing scale. This weighing scale is allowed to weigh, so I shouldn't use it like this, like a weighing scale like this, which gives a number. So you put any polynomial on this weighing scale and it spits out a number. That's what a weighing scale is. You design a very clever weighing scale which does the following, which has the following features, that you take the hard polynomial that you want to show is not easily computable by the smaller model. When you put it on this weighing scale, it gives a humongous number. Yeah? But when you put any polynomial computed by this model of computation, let's say depth 3 formulas, when you put it on this weighing scale, it gives a very tiny number. And then this kind of differentiates all the polynomials computed by depth 3 circuits versus the hard polynomial. So if you are alleging that this hard polynomial were indeed computable by this small model, weaker model, then shouldn't it have thrown a high number for at least some of them, right? So this is how one differentiates. So differentiating measure is sort of the clever part of these proofs often, and it relies heavily on linear algebra. So it basically often boils down to computing rank of certain spaces. So that's one, but of course there are many other kind of results. This is again the slice that I'm most familiar with, but there are many other techniques as well. There was a second question. Average case lower bounds. So not exactly average case lower bounds. So that's a plain and simple answer, but there is like this whole lifting from Boolean setting, proving results in the algebraic setting. So you want to do things like, what does pseudo-randomness mean in the algebraic setting? And then how do you build objects in the algebraic setting that mimic the behavior of, philosophically behavior of the objects in the Boolean setting and things like that. So there's a lot of back and forth that people are trying to do. But a specific average case lower bound, I'm not aware of, but is there one? I don't know. Neeraj? No, I'm not aware of it at least. Yeah.
And now I invite Rutvi to present a token of appreciation as a tradition of ACM. ACM will be planting, has done tie-up with the 14 trees. They are one of the sponsors. So with your name, there will be tree planted near Pune, and it will be nurtured, and you can track the growth. You will get dashboard on your mobile.